Hey everyone, this is Will. Welcome to miniKanren uncourse hangout number 26. Last week we had a great hangout with Chris Martins where she told us all about linear logic and games. That was very popular. Now we don't have Chris Martins, so we're not as popular, alas, but that's fine. We've got a bunch of die-hard miniKanren and relational programming, logic programming, and functional programming folks here, and we're going to play around with some things. We're going to start out today with the while language. So I've been working with two other people at Utah, Michael Valentine and Matt Might, on this while language. And I'm going to show off a little bit about the sorts of things we can do with the interpreter for this while language, and then also show sort of where I get the semantics for this language. This language is also similar to a language called imp, I-M-P, an imperative language, which you see these two languages used a lot for basically for sort of formal reasoning about programming and things like static analysis and doing formal semantics, things like that. You often see a language like while being used. So it's sort of like this toy core of imperative programming in a way similar to how lambda calculus is, you can see that as a core of functional programming languages. You can see something like while as a core for like a minimal imperative language. So you're going to have while loops, we're going to have variable reference, we're going to have assignment, mutation, sort of like a setbang in something like scheme. And we're going to have arithmetic and Boolean expressions and that sort of thing. And then you can build on top of while, you can add all sorts of things. You can add procedures, you can add, block scope, lexical scope, dynamic scope, all these sorts of other things that you might want to add to a language. But we're just going to start with a very, very simple language, simple version of while, where we've added one extension, which is an error handling mechanism called abort, which will abort the computation. And we'll take a look at what we can do with while and show some examples. And I know Orchid has a shiny new extension to Orchid's miniKanren implementation, which involves finite domain constraints. So maybe Orchid will be able to play around with these sorts of examples. We're just using Olig numerals, Olig arithmetic, that's in chapter 7 and 8 of the Reason Schemer for arithmetic. And while that's more efficient than piano numerals in many cases, it's not going to be as fast as a dedicated finite domain solver for arithmetic. So I'd be curious to see how Orchid is able to do with this. So basically, the plan for this part is we're just going to look at a book by Nielsen and Nielsen on semantics and try to see where the semantics for this while language came from. And then we'll look at the interpreter and we'll put it through its paces, and we'll try doing some things like running the while program backwards, or writing the interpreter backwards for a program like factorial. And we can try doing some things like symbolic execution, which is a way to try to see if you can reach certain conditions or states or locations in the program, and if so, what would be the initial values that would let you reach this point. And also try to do maybe a little very simple code synthesis. Okay, so those are the things that we're going to start out with at least, and hopefully after that we'll have time to move on to dealing with the first class macros. So have to keep us moving ahead with this. All right, so it's time for screen sharing. All right, got a little chat window up, and let's take a look at the language of while. right, so this is page 23. It's fine. The book that we're going to look at here is called Semantics with Applications: A Formal Introduction by Nielsen and Nielsen. And this book is available online. So it was originally published in 1992 by John Wiley and Sons, and there's a revised edition from July 1999. This is online. You just look for, just search for it. You'll find it. Also, there's this website. You can find a reference to it, and I'll put this in the links as well. This is a really nice book. I like this book a lot. It's an undergraduate textbook on semantics, and I like it because it's just very straightforward. It's not. I think it strikes the right amount of math and formalism for trying to introduce these ideas. It's not overly formal, but it's but at the same time you can learn a whole lot from it. So anyway, this book uses while as the running language, and you can see. Oh, the link in the paper doesn't actually work. Okay, thanks, Greg. All right, well, just Google for Semantics with Applications: A Formal Introduction, and I'll put a link online. But if you look at the contents of this book, you can see that. Here we go. Yeah. You can see that the while language is all over the place because the entire book is based on the while language. And the nice thing about this book is it shows you different types of semantics using the same language. And in the intro of the book, they talk about how, or in the preface of the book, they talk about how many books on semantics will talk about one type of semantics, like denotational semantics, operational semantics, or axiomatic semantics. And they'll talk about that type of semantics with different languages. But it means that it's hard to understand what the differences are between the different types of semantics. So this book takes the opposite approach. We're going to use this while language, same language for everything, but we're going to look at the different main classes of semantics, operational, denotational, and axiomatic semantics, using the while language, and then using extensions to the while language that are appropriate for each type of semantics, and trying to show when you would want to use each type of semantics, and also trying to drive the point home that it's not like these semantics are competing with each other. It's more like you might want to use different different semantics for the same language to try to prove or reason about different properties. So it's a very nice book. I like it quite a bit. And so let's just try to look in here. Get to. Okay, here we go. So for the while language, there are basically three parts to the core while language. Two of the three parts of this interpreter we're going to write are going to be, and we're starting out here with an operational semantics. Two of the three parts are going to be expression languages. So we're going to have a language for arithmetic, and we're going to have a language for Boolean expressions that can give us true or false. So the arithmetic language is going to just give us back numbers, in particular integers. And so we've got a little language here in table 1.1 that tells us how to calculate the values of arithmetic expressions. So for example, if you have a number, so A's, you can think of this as an interpreter. It's basically what it is. It's an interpreter for an expression language. See if I can zoom in a little bit. Okay. So we can call our interpreter for the arithmetic language A, let's say, if we were defining a scheme or racket function. And so we've got an arithmetic language A, or an interpreter, called A, and it's going to take an expression as the first argument, and it's also going to take a store as the second argument. And if you wanted to, you could pass these in separately. You could pass in the expression before the store and that sort of thing. So you could do some partial evaluation if you want. But in this first case, if their expression is a number n, and we have any store, and a store is like sort of like an environment, but one where you can mutate and update it. It's a mapping between variables and values. So if we have just a number literal like an integer, literal like 5, then basically we just get back the number that's represented by 5. And if we have a variable, x, which in Scheme we might represent as a symbol or something like that, then we apply the store to that x. So we're doing a lookup. So this is very similar to what we would do in just like a Scheme interpreter. So if you have a number, this value is to itself. If you have a variable, you just look at the variable up in the store. And then if you have an addition expression, A1 plus A2, or A1 and A2 are arithmetic expressions, then you have sort of the standard natural recursion where you're going to recur and evaluate A1 in the current store. You're going to evaluate A2 in the current store and then add up the values using some implementation of addition. And similarly for multiplication, which they use the star for, and subtraction. And in their language, I believe they actually have negative integers. Currently, in my implementation I've been working on with Michael and Matt, we don't have negative numbers. We only have non-negative integers. But anyway, this is just like a little arithmetic expression language. This is very easy to implement in general. In miniKanren, of course, if we want to write a relational interpreter, it gets a little trickier because we have to somehow deal with arithmetic in a relational way so that the stuff runs backwards. So if you say, hey, you have some arithmetic expression and it gave you 12, well, what are all the ways you could have gotten 12? And maybe you did some additions, or maybe you did multiplication, or whatever, right? So, but we have different ways of dealing with arithmetic in a relational way in miniKanren. We can use piano numerals. We can use the Oleg numerals, that described in Reason Schemer, or we could use the finite domain constraints we see in cKanren and that ORCID has in the new miniKanren implementation, and so forth. So there are different ways to do this, and they have different trade-offs. The implementation I'm working on uses Oleg numerals and Oleg arithmetic for this stuff. Okay, so that's the arithmetic expression languages, and that's very straightforward. There's nothing special there, except for the fact that we have numerals, right? So numerals are the arithmetic. Arithmetic's the thing that's kind of a pain for us. All right, and let's see. Okay, so here's the next language. This is also an expression language, this B language. In this language, it's for Boolean expressions, so we're going to get true or false back. And so you can see that in the semantics, true is the expression, and when that's evaluated in any store, that gives you back some true value, which in this language is TT. The semantics is TT, and then false evaluates to this representation of false, FF. We have equality over numerals, over numbers, and you can see that these are arithmetic expressions. So the equality in this language only works over numbers, and we can see that we're going to evaluate using the arithmetic language A1 and A2, and then compare to see if those numbers are the same. And if they're the same, you get back true. If they're false, you get back false. We also have less than or equal, which works on numbers again. And we have Booleans. We have negation, not, that works on Boolean values. And we have and, which works on Booleans. So those are so this is our expression language. And this language, once again, is easy to implement in miniKanren, with the exception of the fact that we have to do this arithmetic stuff. But we can use the same systems for relational arithmetic to do this comparison that we would do normally when we are dealing with arithmetic. So this is really about the arithmetic operators being a little tricky to make relational. But otherwise, it's all fine. Okay, so that's arithmetic and Boolean expressions. So now see if we can get to the actual statement language. I can do it. All right, here we go, operational semantics. We're going to look at, and this is an important point up here, by the way, where it talks about two types of operational semantics. So operational semantics, one of the three main types of semantics, along with denotational semantics and axiomatic semantics, also known as horror semantics, after Tony Hoare. So for operational semantics, there are basically two big variants. And what makes the semantics operational is that basically the semantics tell you how to execute how to execute the language in some sense, like either as like an interpreter or as a small step machine or something like that. And there's sort of two main flavors of operational semantics. One is natural semantics, which is big step semantics. These are the interpreters that we've been writing in miniKanren, or the traditional sort of Lisp and Lisp metacircular interpreter. These are big step. You have an expression and maybe an environment, and you get back a value. And then there's another approach, which is small step, also called structural operational semantics, where you're going from one configuration to another configuration until you can't go any further, and that's your final configuration if you reach one. And they have different trade-offs. The book describes the trade-offs in a nice way, but we're doing the big step natural semantics. Also, the natural semantics are also called relational semantics, which I like, because we're really looking at things from a relational standpoint. So we're going to do the natural semantics. So if you want to look at the book, that's what we're doing. All right. So here are the rules, the natural semantics for the WILE language. So let's take a look at these real quick. Orchid says that in the book Software Foundations, they also use the same language, the WILE language. Yeah, that's not surprising. So WILE or imp, which is got a WILE-like feel, these languages come up in many, many semantics books. Very, very standard sorts of languages. Just like if you were looking at a book on functional programming, you wouldn't be surprised to see the lambda calculus. If you look at a book on imperative languages, on formalizing those, you wouldn't be surprised to see WILE or imp. There might be slight variants, but they're going to be very similar. Okay, so this is sort of the interesting part. The arithmetic language and the Boolean language, those are very similar, basically the same exact thing as we would do in Scheme or in miniKanren interpreter. If we wanted to handle arithmetic, if we wanted to handle Boolean expressions, we'd write that exactly the same way in Scheme. But the WILE language, that's a little bit different, because this is not a functional language. This is a very bare bones imperative language. So the first thing you see is an assignment. And you can see there's this sub-NS telling you this is a natural semantics, and in brackets are the names of the different semantics rules. So here we can see what a configuration looks like in our system. So on the left of the configuration, you have a statement, and on the right of the configuration, you have a state. And the state is the mapping between the variables and the values. And this can be destructively updated. We can change, if x is 5 at one point, we can make x 6 at another point in time afterwards through this assignment operator. So this is assignment. It's like we all know and love or loathe from C and Pascal and things like that, or Java or whatever language, Python. So here we have an assignment. We're assigning to the variable x the value of the arithmetic expression a. So in this language, we're only going to have numbers or Boolean values, really, that we're dealing with. And our assignments to variables are only going to be numbers. So we're only going to assign numbers to variables in the store. And the result of our computation is going to be a store. So we're going to get back a store, which is sort of like an environment that has all the mappings between variables and numbers. And that's the result of our computation. Whereas with our big step interpreters for a language like Scheme, we get back some final value, maybe a list, maybe a number or something like that. We don't get back the environment. We get back a value. But here we're going to get back a store mapping variables to values. Okay, so what this rule is saying is if you have a configuration that has as a statement as an assignment of x to the value of the arithmetic expression a and store s, what you have to do is update the store. We're basically going to update the store with a new binding between x and the value of the arithmetic expression a within the current store. So basically, we're going to evaluate a is some arithmetic expression, with respect to this current store s. That's going to give us back a number, and then we're going to add to the store a binding between x and that number. And if there already is a binding between x and that number in the store, we're just going to clobber the old value. Okay, this isn't like an environment where we shadow it and then, lexically, if we leave that scope, we see the old value. No, we're just clobbering it. We can just set bang it, essentially. All right, so that's the assignment statement. Skip. If we have a skip statement, that just means if you basically that's like a no-op. We're not doing anything. So if we have a skip instruction or statement within some store s, we just return the store. So you can see this first expression, or this first statement type is returning a store. The second statement type is also returning a store. All of these statements are going to return a store. So skip is like a no-op. We just get back the store back. Get the store back. Here we have composition as the third type of instruction. So we have S1, statement S1 composed with statement S2 using the semicolon operator. That means we're going to do S1, statement S1, and then do statement S2. And we're running this compound statement with respect to some store S. So how do we do that? Well, basically we create a configuration containing the statement S1 in the store S. We run that, and we'll get back a new store S prime. And then we run statement S2 in a configuration containing the store S prime, and we get back S prime prime, and that S prime prime is the value that we get back. So we're just threading this store through the computation monadically, if you know that term. Okay, so that's composition. Now we have if true, and then we have if false, so we have two different cases there. So here we have a configuration that has an if statement. Okay, this is an if statement, not an if expression. So we're basically we're going to evaluate using our Boolean expression language the Boolean test B, and if B evaluates in the current store S to be a true value, that means that we're going to evaluate S1. And so we're running the statement S1 in the current store, and we're getting back some new store S prime, and that's what we return. And similar case, when the Boolean expression is false, we run S2 instead. Okay, that's all that says. No problem. And then while is it's also actually pretty straightforward. So there's two cases for while. What a while statement looks like is like this. You have while some test B is true, do some statement. And we're just basically going to repeat that statement S over and over again while B is true. If B ever becomes false, we'll just stop. So if we look at this while statement, if we evaluate the Boolean test B in the current store and that gives us a false value, then we just return the current store. So then it just behaves like skip, basically. This is just like skip. If the test is false, we just return the current store without doing anything. If, however, we evaluate the Boolean test in the current store and we get back a true value, that means we have to run the statement S, and we have to go back and try the loop again, because we might keep doing it some more. So what's going to happen if we run the statement S in the current store S? So there's big S and little s. So the statement S in the store S, we're going to get back some new store S prime. And then we're going to run the while statement again. Notice this is exactly the same while statement, but the configuration has changed. The overall configuration has changed because we have a store S prime instead of our initial store S. And this will give us back some new store S prime prime, if we don't go in an infinite loop, that is. And that S prime prime store, that's the value we're returning at the end. Okay, so every single one of these statements is returning a store, and we were using this Boolean expression language for both if and for while, and we're using the arithmetic expression language for assignment. Okay, so that's why we need those sub-languages, which are just standard expression languages. But this is the statement language. This is the part that's imperative. This is where we have assignment, like this x gets a, and we have if statement and we have while statement. Okay, and this is enough to do all sorts of interesting programs. It's very easy in code factorial. You'll notice what's missing though. We don't have any way to introduce new variables. There's no binding form in this language. We don't have anything like lambda or let or leprac or anything like that. So how do we actually run a program? Well, basically, we do two things. In the semantics for this version of while, if you look up a variable and it's not bound in the arithmetic language, then by default, that variable is bound to 0. So one way to look at it is every possible variable is already bound. It's just that by default they're all bound to 0. And if you don't want it to be bound to 0, you have to state that explicitly. So all the variables are already bound. The other thing is that notice that each of these configurations for the while language, the actual statement language, has a beginning store, has a store coming in. So the way you actually write these programs, if you're just using the minimum core language, is you just set up the initial store to have whatever bindings you want for your variables, and you run it that way. So if you want to do factorial of 5, you have a little language in the statement language that allows you to express factorial, and then you just make sure that in your initial substitution, you have x bound to 5, let's say, and y bound to 1 or whatever. You only need to bind y to 1. You could do that in the code as well. But you would just say, if you want to take factorial 5 and or factorial of x, and x you want to be 5, you just put that in your initial store, and then at the end of the computation, you'll see what the values of x and y are in the output store. So that's how you do something like factorial. Okay. So that's how you read these rules, and the book goes through and explains this very nicely. So if you ever want to learn about semantics and have had trouble, I really recommend this book. I like it a lot. Very readable. And so now what we're going to do is take a look at these semantics and miniKanren, and just maybe see how one of the rules compares, and then let's try doing a couple examples. All right, so let's bring up a while language here. And oh yeah, so there's one more statement that I haven't talked about that we're also going to add, and that's abort, which is basically an error statement. It's going to be sort of like skip. When we have an abort, that just means we're going to stop the program and return S. But the difference is if you have an abort inside of a compound expression, inside of a sequencing with a semicolon, you just stop right away, right? Whereas with skip, you would still continue. If the S1 was skip or were skip in a compound expression, you would still do S2. But for abort, you just stop immediately. So that really is a way to get out of a computation. Okay, so let's take a look at while with abort. And this is the using a faster version of miniKanren that Michael Ballantyne's been working on, and that's on his GitHub repo, and I'll put this online as well, a link to that. But basically, we're just going to do a couple things. We're loading miniKanren, and we also have we're also loading the numbers. Okay, so this is the arithmetic system, the relational arithmetic system, the Oleg numbers. We're going to be using a tag representation of numbers actually in the interpreter. We're going to tag our numbers. So in order to make that a little less error prone and a little easier to write, I wrote this little num helper that will just create a tagged list with the num tag, and it's going to construct an Oleg number, which are these little Indian binary list things. Like an Oleg number, 1 looks like this, 0 is the empty list, and it's sort of reversed order. So this is 2, and this is 3, and 0, 0, 1 is 4. So this is a binary representation using lists where the last digit in list is the most significant digit. That just makes the implementation of the arithmetic system a little simpler. That's what an Oleg number looks like. And the numbers we get back from this num function are going to be tagged. So if I called num of 4, what I would get back is this number, but it would be tagged with the num symbol, and it would look like that. Okay, so this is what the number 4 is going to look like in our language, right? Obviously, if we were using the finite domain constraints that we have in something like miniKanren or that Orchid just added, then we would be able to use just the Arabic numerals, and that would be easier to read. Okay, so that's a trade-off there in terms of readability. So that's what num does. The store lookup. This is just going to look up the variable x in the current store and give you back a value. Okay, so if x is bound to 5, we're going to get back 5 as value. Or I shouldn't say get back, because now we're in the relational world, so val would be unified with 5. This is just a normal environment lookup. The only thing that's different is we have a special case for when the store is empty. Normally, when we're doing an environment lookup for an interpreter in miniKanren, if the store is empty, we just fail because the value is unbound. Or if we want to explicitly represent errors, we might have an explicit error saying that the variable is unbound. But in this case, given the semantics of while, if the store is empty, that means that we're actually going to return 0 as our number. And so every variable is bound implicitly to 0 unless basically there's some shadowing going on, saying it has a value other than 0. Otherwise, it's just a normal variable lookup. Not in storo, this is, we've seen before, is like not in invo. This is just enforcing using disequality constraints that the variable x is not present in the store s. We need that just to make sure that when we're doing our store update, our cases are not overlapping. So there's nothing really interesting about this. We're just cootering down list s and then applying the disequality constraint as we go. And that's it's exactly the same as not in invo if you've seen the relational interpreters before. Update store. Oh, that's going to take a variable, a value we want to make sure that the variable is bound to, an old store and a new store, which is s out. And here we're just enforcing that the variable coming in is a symbol. Indeed, is a symbol. And we're going to do one of two things. So we're going to either replace x to have the value v in s to give us a new store s out. In this case, the replaceO is assuming that x is bound already, and not just bound to 0, but has an explicit binding. So here we're just replacing the current value of x and saying, if x used to be 5, now maybe if v is 6, now x is 6. So this isn't a true replacement. It means that x already had to have been explicitly bound in the substitution. In the other case, we're using the not in storo constraint to express that x isn't already bound in the store. That means that x is implicitly bound to 0, but it's not explicitly bound. In that case, we can just extend the store with binding between X and V. Now, we really, if we wanted to treat the store more like a traditional environment in our scheme interpreters, we could just go ahead and extend the store with a binding between X and V and not worry about whether or not X is already in the store. That doesn't work so well, though, because in general, when we want to run these computations backwards, we don't want to have to figure out exactly what the order of the extensions were to the store and all that stuff. We just want to say X is 5. We don't want to say, well, X is 5 now, and in the old store before that, X used to be bound to 4, and so forth. It gets very complicated. So much better to actually do a real replacement. It makes it much easier to express the computation when running backwards, and it makes it easier to read things, because if you have some while loop that adds 50,000 bindings for X, not only is it less efficient to have these giant lists, but it's also, why you don't want to read that as a human. It's very messy stuff. So we'll make sure that each variable only has one binding in the store. And this is the replacement code right here. And basically, we're just looking through the store, and when we find the variable we're looking for, we're going to replace it, and if not, we're going to cons up the list. We're going to basically re-add the part we already saw, and then keep going. Actually, I could probably make that a little more efficient. I could probably bind this y.v to a variable. Anyway, doesn't matter. Anyway, so replacement is just this is very similar to how you would write replace in scheme if you wanted to replace the first occurrence of some pair in association lists. All right, here's the A0 language. And by the way, so all this stuff dealing with the store, this is definitely the most complicated part of the system, I think. And it's not even that complicated, but the rest of it's very straightforward, I think. So we have the arithmetic language interpreter. So we have an expression, we have a store, and we're going to get back a number. If we have a symbol, we're going to treat that as variable, and we're going to look up the variable in the store. Okay, fine, standard. If we have a tag numeral or a number, then we're just going to return the number. Okay, the number evaluates to itself. If we have an addition, for adding expressions A1 and A2, then we evaluate A1 and we evaluate A2 in the current store. We should get back numbers, basically N1 and N2, these Olig numbers, and then we should be able to call the Olig arithmetic version of plus to get the sum of those two numbers, N1 and N2, and we have to re-tag. We have to remember to re-tag the Olig number to get a number in our system, and that's what we end up with. I guess I should have made a call to, no, anyway, I was a little sloppy here. I think I put on the explicit tags. I could have called my helper function. And we have subtraction, we have multiplication. Those work exactly the same way. And here is a to-do about using finite domain constraints, which Orchid just added to Orchid's implementation of miniKanren. There is one thing here that I want to point out. Here we're evaluating the sub-expressions, A1 and A2, before doing the addition. And that makes sense, certainly when running forward. However, if you're running backwards and you know what the sum is, the output, right, but you don't know what the input expressions are for A1 or A2, or maybe for either one, you really want to have the plus O coming first, probably. And if you're doing finite domain constraints, you should be able to get away with that and still have good divergence behavior. But because we don't have finite domain constraints in the version of miniKanren I'm using, can't really put the plus O up above the recursive calls. But I think that's the right place for it to go if you have finite domain constraints. And maybe Orchid could verify that. Daniel asks, and the store can't change in any of the arithmetic operations, correct? That's correct. That's a good point. So actually, the way to think about it is for the arithmetic operations and for the Boolean operations, for those expression languages, it's an expression language because those can only look up variables in the store. They can't modify the store. In fact, the Boolean language only indirectly would look up a variable in the store. The arithmetic operation language right here, this is the only place you have variable lookup. But there's no store change or store extension in either the arithmetic language or in the Boolean language. So this is a very, very simple sort of interpreter. This is sort of like a calculator interpreter. It's not really interesting other than the fact that once you want to do arithmetic in a relational way, then you have to figure out which representation of arithmetic you want. And the Boolean language is probably even simpler. Basically, if you have a true expression, then you get this hash, the TT. I tried to be similar to how the book represented true and false. So true evaluates the TT, false evaluates the FF, and we have a not. You know, and here I'm just putting the condy before the recursive call because in some cases that can be more efficient or cut off an infinite loop. In general, you always want to make sure unifications come before recursive calls, so that's what I'm doing here. But obviously, you know, if you had a true value, then the not of that, the negation of that's false, and if you had false, the negation is true. And I put the value first because I'm perverse, whatever. And then we have and. And is a similar thing. I don't know why I didn't put the condy up front. I think this was a little bit faster, it turned out in practice in the test suite. You could definitely put the condy above these two B's, zeros. Because they're nested condies, I think you have a bunch of branches. So when writing forward, this is faster, but when writing backwards, you might want to have the condy above. I'm not sure about that. Okay, and here we have equality. So we're going to call the arithmetic interpreter on arithmetic expressions A1 and A2, and that should give us back numbers. If not, it should fail. And if the numbers are equal, they unify, then we get back true. And if they are not equal with the disequality constraint, then we get back false. So numeric equality is fine. It just has to call the arithmetic operators. Now we have less than, and I have both less than, equal to. I think in this book they only have less than equal to, but I found it sometimes convenient to have less than as well. You know, obviously if you have less than and equal, you can write less than equal if you want, but I just went ahead and added both. Anyway, I'm just calling the arithmetic operators on A0 and A2, and now I'm calling the Oleg number implementation of less than and less than equal. So standard sorts of things, if you're familiar with the relational arithmetic, there's nothing interesting there or surprising. There's this with abort thing, I'll talk about that in a minute. And then here is the actual interpreter for the while expression, or while statement language. So here we have a configuration, and then we have an output, which is going to be a store. And like I said before, the configuration is a statement, like this if statement, followed by a store. So configuration is two parts, a statement and a store. And the way I represent it is I always put it in a list just to kind of keep things tidy. Skip really doesn't have to be in a list, but I want it to be as uniform as possible. So here we have the skip expression, and we can just see how these rules correspond. You know, if you have a skip statement, sorry, skip statement, not a skip expression. If you have a skip statement, and you're in store S, you just return S, and that's basically what we have. We have a skip statement, we're in store S, and the output is S. That's it. You know, it's pretty straightforward. We'll come back to abort in a minute because it's got a special rule. Well, actually, you can already see what the abort does. You know, if you have abort in a statement, then the output is, instead of just being S like in skip, the S, the statement. Or sorry, the output is actually tagged with an abort. You could also do this by like tagging this version, the normal version of getting something back, with like a val instead of an abort. So the val you get back is S, so we could write this as like val S instead of just S. And that way we could easily distinguish between values and aborts just by doing the unification. Here we're using a disequality constraint when we don't want an abort in the answer. The tagging might be better, might be faster. It's cleaner in a sense, probably. But anyway, we didn't want to have to tag everything else, so we're just tagging the abort substitution. So the reason we want to tag this is so that if we want to run things, well, the two reasons. First of all, so we can detect when we have a abort condition and just sort of pass that substitution through the rest of the computation without doing anything else. The other thing is if we want to run backwards and say, hey, I want to generate some code that would make me abort in this position, we can do that also explicitly. Here's assignment. So, assignment over here, if x is being assigned to a, we have to look up a, or so we have to evaluate a in the arithmetic expression language with respect to the current store s, and then we update the store with this binding between x and the value of a. And you can see we're doing something similar here. So we're calling the arithmetic expression evaluator on a to get back v, and then we update the store. That's very simple. And then the updated store is the output value. We could simplify this code a little bit by replacing s hat with out if we wanted to. Doesn't really matter. And similarly, if abides by the same rules as before, we have a Boolean expression, evaluate that. If we get back true, then we evaluate s1. Otherwise, get back false, then we evaluate s2. Sequencing, very simple. If we have s1 followed by s2, we evaluate s1 in s. And then if that succeeds, then we're going to evaluate s2 in the store we got back from s1. Notice there's this with abort thing wrapped around evaluating s2. That's so we can handle abort. Basically what this does is that if s1 ends up calling abort somewhere, instead of actually running s2, we're going to go ahead and unify the store we got out, which is s hat, will be some sort of abort store, store with abort wrapped around it. We're just going to go ahead and unify the out with that store, that tag store, instead of actually performing s2. So this is a way to short circuit evaluation and not actually do s2. Okay. And then Michael Ballantyne came up with this mechanism based on reading a paper on trying to bridge the gap between big step and small step interpreters that had a very similar idea of passing through the computations. I will also add a link to that paper. I forget off the top of my head who wrote that, but that's a nice paper talking about how to make your interpreter handle things like abort in a nice way without having to go to small step, because big step has some advantages over small step in some cases. And then we have while, and so we're going to evaluate the Boolean test. It always kind of sucks when you have to make this recursive call before these unifications, and I've tried inlining multiple calls to B0 inside this branch and inside this branch. It seems to slow down the tests in practice. Anyway, if the Boolean test is false, that means we're done. So we just return s as the output. If the Boolean test is true, that means we have to run the statement s at least once. So we run s, and then we're going to run the while expression again, except in the output, this s hat store. And once again, we use with abort to make sure that if when running s we aborted, then we're going to pass along that specially tagged substitution, or sorry, specially tagged store without actually running the while again. So basically, if we ever error out, we're going to wrap around the current store, the abort tag, and just thread that through the rest of the computation without actually running any of the computation. We're just going to basically do treat the rest of the program as no ops and just thread through the store. And that's exactly what this with abort macro does. So we can see what one of the uses of with abort looks like. So let's look at the sequence. So what with abort takes is an input store. That's what in is. In is a store. And it takes the output store that you want, to unify with at the end, and then it takes one or more body expressions which have to be goals. So in this case, it's a call to our statement reducer, and our macro here just makes a call to this function called with abort, and basically that's going to wrap up all of the mechanism where we have one of two cases. Either the abort tag isn't present in the input store, which means that we had an honest-to-goodness store coming back, in which case we actually run the goal that we've wrapped with abort, or the store coming in actually is an aborting store, and in which case we don't run the goal G, we just go ahead and unify the output store with the input store. And this would probably be cleaner, and it might be faster too, if we tag the value stores and in addition to the abort stores. This probably is something worth trying to see if that speeds things up. But that would get rid of this need for absento. And in fact, I think that's the only use of absento in the whole system. So that's a little unfortunate. Could easily get rid of that absento call by just tagging the regular value stores as well. Okay, so that's the full implementation of the system. It's not particularly long, and it's not very complicated in a sense. I think the way we're handling the abort is a little subtle, but it's not. Once you understand how it works, it's not a big deal. And then most of the trickiness is either handling arithmetic relationally, which we just have to decide how we want to do that and use one of the existing libraries essentially, or the other trickiness is updating the store, making sure that we're replacing the value instead of just extending it. That code, it's not particularly subtle. You just have to remember when you're doing the environment lookup, the store lookup, that by default all the variables are bound to 0. Okay. That's it. That's the implementation, and I'll have a link to the implementation too. All right, so let's look at some tests here. So we don't want to look at these right now. We want to look at while tests. All right. Okay. So let's look at factorial. And this is the definition of factorial in the book, the Nielsen and Nielsen book, which is actually, as far as I'm concerned, incorrect because it doesn't handle factorial of 0. It only handles factorial of numbers greater than 0. But the idea here is you have a sequence of expressions, and first we're assigning y to be 1. So the end result, we're going to see what y is bound to. So if we're taking a factorial of x, say x is 5, at the end we're going to see the value of y in the store. And the assumption here is that we're going to start out with a store that has a value for x that's not 0. Okay, so we're going to set y to be 1. And so obviously, if you're a Lisper, you like the syntax, but if you like languages like Python, this might be a little hard to read. This is basically the abstract syntax tree that we're looking at in this program. Set y to be 1, and then we have a while loop. Basically, we're saying, well, while x is not equal to 1, then we're going to execute this statement, which is another sequence of these two assignments. So while x is not equal to 1, we are going to update y, and we're going to update x. So I guess if people like infix notation, the program would look something like this. It would say, y is 1 in the beginning, semicolon, while not x equals 1, then we're going to say y gets y times x, semicolon, x gets x minus 1. Okay, so this is what it might look like in a infix language. You forgot. Oh, you found the bug in the book. I consider it a bug because I think factorial should work for 0, or for factorial 1 should work as well, and factorial 0 should be 1. So yeah, so I consider it a bug, but maybe they didn't. But anyway, so that's what their version of factorial looks like. Okay, and the idea here is that we're going to start out in some store where x starts out as 5 or something like that, right? And after this thing runs, we're going to end up with a store where y is 120 and x has been decremented until it's down to 1. So that's this is the input store, and this is the output store. Okay. And as long as you pick an x greater than 0, then this works just fine. I've got a slightly different version, which I call the correct version, which handles 0 as well. Basically, I just have an extra stop condition. So, if x is 0 or x is 1, we don't execute the while loop. Yeah. So basically, very, very close to the same thing. It doesn't matter too much in terms of the actual ideas. But here is, let's find a factorial. Okay, here we go. So here are some factorials. Let's find like factorial 5, let's say. All right, so here's the call to the reducer for the statement language. And this factorial program is what we were just looking at. Okay, so instead of inlining it here, I'm just calling the globally defined version of factorial. And we're seeing we're starting out with a store where x is bound to 5. We don't have to bind y to anything because the code for factorial already does that. Let's see. Yeah, so we can see that y is bound to 1 initially in the code itself, and initially y starts bound to 0, of course. And then we can see at the end, when we run this test, we get a y bound to 120 and x bound to 1. So that's the test. So let's see if we can actually run this. Okay. I think I've changed the order of some things, so some of the tests are doing the answers in different orders, but we should be able to try this quickly. So let's try just running this forward. All right, and so this beautiful list right here is our representation in Oleg numbers of 120, and basically my num constructor will give us the tagged version of that. So this is the output store. Whoops. So the output store, we're saying y is 120 and x is 1. Okay. So we can run it forward. If we were using finite domain constraints, the numbers would be easier to run, or easier to see, but the idea is the same. And of course, we can play some of our usual games, like we could put in the query variable. We could say we don't know what the input store was, right? But we know the output store should bind y to 120 and x to 1. So can we figure out what the input store was? I got to tag that, or sorry, put a quote. And sure enough, it says the input was 5 in Oleg numbers, right? And if we do a run 2, I think this diverges, but I'm not sure. No, actually. All right, so, whoa, what? Oh, interesting. So it's saying we could have either explicitly bound y, or we could have left y not bound at all, in which case it would have been 0. So yeah, those are both correct answers. I didn't realize there were 2 answers. And a run 3 now, run 3 seems to diverge. Okay. If we were using finite domain constraints, a run 3 might not diverge. We might actually be able to find that thing. So we can run forward, we can run backwards. We don't have particularly good reputation for completeness when running backwards, factorial at least, but we can run factorial backwards. So what else can we do? Well, so one thing we can do is try to do some program synthesis, like a little bit of program synthesis. So, okay, so here's one. So basically what I'm doing here is I'm taking, I'll look at the correct version. So I'm taking the equivalent of the code for what I'm calling the correct version of factorial, and I'm removing the while test, this and not blah 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 thing. Basically, we're saying x is not 0 and it's not 1, and since we're only dealing with negative or non-negative integers, this is the same as saying that x has to be greater than 1 or x is greater than or equal to 2. It's the same thing. But anyway, so I've removed the test and put a logic variable in place of the test. And the question is, can we infer the missing code given a whole bunch of examples? So this is an example-based synthesis. We're trying to fill in the missing code from a bunch of example calls. So here we're saying, okay, so we get this whole snippet of program, and if I call that with x is 1, I should get back y is 1. That's factorial 1 is 1, factorial 2 is 2, factorial 3 is 6, factorial 4 is 24. So I'm just trying to give a bunch of examples and see if I can infer something. So here, notice I left out a test for when x is 0, right? I don't have a test for when x is 0, and so the test I got back is saying that x can't be 1. And in fact, that is the exact code that we get for what I'm calling the incorrect version of the code. So we can try adding that test. So let's try adding a test for when x is 0. When x is 0, then x should still be 0 at the end, but y should be 1. Factorial 0 is 1. So let's see if we can get back anything here. And one thing I've noticed is that it seems to be important how you order these tests. And if I remember correctly, moving this test for 0 down a little seemed to help. Let's see if that makes it any faster. Okay, so it comes back after a couple seconds, and it's saying that x has to be greater than 1, and that's exactly right. That's exactly right. So it's a different test than we started with, but it's equivalent, given the fact that we don't have negative integers in our system. So I was able to find that snippet that was missing based on the examples and sort of a hole in our code. But it took a couple seconds, and we're not inferring the whole definition of factorial. Clearly, we're just looking at the test. But we can do a little bit of example-based synthesis there. And then, probably more interesting is this is kind of like the last thing to show off. We can do some symbolic execution. Some symbolic execution. So let's see if I've got the slides. Well, I'll grab the slides, I guess. Okay, so these are from slides by Stephen Chang at Harvard, and apparently some of these examples are based on Jeff Foster's slides, so I'm not sure if this particular example is from Jeff or Stephen, but anyway, here's the example we're going to run, and this is a form of what's called symbolic execution. So the idea is we have some program, and usually when you see symbolic execution, you see this for imperative programs. You see it for programs like C, that kind of thing. Okay, so here we have a little language. This looks a lot like our while language, right? Here we're saying that we've got some integer variables A, B, and C, those are integers, and all of our variables are non-negative integers, so the types kind of don't matter. But we're saying that A has some initial value alpha, B has some initial value beta, and C has some initial value gamma, right? So these are sort of symbolic values. We don't know what those are. What we're trying to figure out in this problem is what the values of alpha, beta, and gamma might be that would allow us to violate this assertion on line 11. So you can see that we also have variables x, y, and 0. They're all set to, x, y, and z. They're all set to 0, which is very much like how while works. So we don't even have to add those variable declarations. And we have some conditionals here. If A is true, so these are sort of like C semantics, right? Where 0 is false and non-zero value would be true. So this is really implicitly, this is like an equality, right? This is saying, you know, if A is not equal to 0, if not A equals 0, then assign x to be -2. The fact that this is a negative number doesn't matter. It could be like 20 or something like that. But x is not 0, basically. So if A is not 0, then assign x to be some new number. And if B is less than 5, then we do another if. So here we have some nested ifs. And here we're trying to say, okay, if both A is false and C is true, so this is like saying if A is 0 and C is not 0, then we're going to assign y to be 1. And then otherwise, we're also within this this outer if, we're going to assign z to be 2. Okay, and then we're going to have this assertion where we're going to say that x plus y plus z is not equal to 3. And what we're trying to figure out is, is there a way to violate this assertion? And if so, what would be the variables, the values of the initial variables? And so x, y, and z, those are already fixed at 0 initially, and those are the variables that are bound, they're involved in the arithmetic computation. A, B, and C are involved in the control flow, right? So these are tests and ifs. So they're involved in the control flow. So we want to figure out, are there values of A, B, and C, or alpha, beta, and gamma assignments, that would change the control flow such that we would get an assignment for x, y, and z that would violate this assertion. Okay, so that's the sort of thing you get with symbolic execution. And you can see, you can basically have some sort of tree type structure, and you're trying to find out, you build up these path condition constraints, and you can call an external solver and so forth. But we can do this in miniKanren as well with the while language. In real symbolic evaluations or symbolic execution systems, they have special solvers. They have special they're doing some optimizations, which we may or may not be able to do in miniKanren, but we can certainly express this problem. And using the finite domain constraints, my guess is we can solve the arithmetic constraints pretty efficiently as well. Okay, so let's see how we might express that problem. So here, basically, I took the code from the slide. And that assert, we're not going to add assert to our language. We're going to use abort and an if that's protecting the abort to do the same thing as the assert, basically. And here is a slightly modified version of that code that we're going to actually execute. So we still have, we're trying to figure out some initial values of A, B, and C, alpha, beta, and gamma. This int x equals 0, y equals 0, z equals 0. Like I said before, we don't actually have to include that explicitly because those variables all start out as 0. And then we have some conditional code. So basically here I just got rid of the negative number and so forth. But I guess to be really accurate, this isn't exactly what we're modeling. What we're really modeling is, so we're getting rid of that line. That's not really necessary. This comment. When we say if A, what we're really saying is if A, if not A equals 0, that's what it's really about. And then down here, I guess I can change the syntax here a little bit. It's sort of like a hybrid language. Here we're saying if not A. So if not A means that not A means that A is false, which means that basically A is equal to 0. Okay. And here we're going to say and C is true. That's the same as saying not C equals 0. I guess we can just use equal signs now because we have special assignment. So here's like assignments. Okay. And then here for this assert, we're going to do this a little bit differently. We're not going to use an actual assert because we don't have assert in our language. We're going to use an if. So we're going to say if not of x plus, because we only have binary addition, y plus z equals 3, then in that case, we are going to abort. All right. So that's really how we're going to write this program. And of course, we also have to do our sequences and stuff like that, right? Because we're basically doing the abstract syntax tree. So this is what the program looks like once you've turned it into our language. And we could write a parser or something like that if we wanted to. It doesn't really matter. The other thing we have to remember is because of the way our if statements work, you know, we often have to have bridges, skips in the else branch, basically with no ops. But anyway, that's what we did, and we don't have any negative numbers, so we just, instead of assigning x to -2, I'm just assigning it to 5. Doesn't really matter. Okay, so now we've got our program in that form, and the question is, can we actually do the symbolic execution? So let's try it. Okay, so let's see what happens here. So here we're going to try inferring the alpha, beta, and gamma. Let's just do a run 1. And S is going to be our output store. Yeah, so we want to run this program, that symbolic program that we wrote, with unknown values in the store for A, B, and C of alpha, beta, and gamma, so some sort of numbers. And we want to make sure that the output store was an aborting store. So the only way to get an abort in the program the way we wrote it, the only use of abort is inside of basically that assertion. It's the same math as for the assertion. So if we get an aborted value back, we know that that was because we violated the assertion. Okay. All right. So that's why the abort value is handy for doing symbolic execution. And if we run it, we actually can find an assignment. So this is giving us back values of alpha, beta, and gamma, and this is the final store. So it's maybe a little easier to look at the store because everything's tagged. But at the end it's saying, you know, we care about the values of A, B, and C, right? So these are the values of A, B, and C. And what it's saying is that A is a number, which is 0, B is a number, which is 4, and C, it actually doesn't matter what the value of C is, except that C can't be 0. As long as C is not 0, then this supposedly works. So let's go back and take a look at the example again. Let's see. So is that right? So it's saying A is 0, A is 0, B is 4, and C is anything other than 0. So let's see if that does violate this assertion. All right. So X, Y, and Z start out at 0. If A is true, well, if A is 0, then that's not true, so we don't do this assignment. Okay, so we skip that. Now so X, Y, and Z are still 0. Now we come down here. If B is less than 5, well, we said B is 4, so B is less than 5, so we're going to do this. Okay. If not A and C, well, not A, because we said A is 0, so not A is true. And if C is true, that means C has to not be 0. Well, that's what our constraint said. It says C can't be 0. So this gets run. So this test is true. So we try to, we go ahead and assign Y to be 1. So we have X is 0, Y is 1 at this point, and Z is 0. And then here we assign Z to be 2. So we have X is 0, Y is 1, Z is 2. And if we add X, Y, and Z up, then we get 3, and we violated the assertion. So sure enough, this is a set of values for A, B, and C that would violate the assertion. And we can actually get 4 of these values. They're basically 4 different combinations here because you can get different values for B. B just has to be less than 5. I think there are 4. I think 1, 5 diverges. Is that right? No, there are 5 values. Okay, and maybe run 6 diverges. Oh, 6 values. Okay. There are more values than I thought. 7 values. Okay. Are there 8 values? Are there infinitely many values? Probably have it C infinitely. Ah. Okay, well, let's see. Are there like 20 values? Let's look at C. See, here it doesn't seem to be doing anything differently. So why? What's going on here? Why is it? Oh! Duh. I better run star terminates. Yeah. So I should take the length of it, right? I thought I was getting more and more values, but no. There are 4 values. Okay. I was just being stupid. No, there are only 4 values. I thought it was going to diverge, actually. So that's why I was worried. Yeah, so it's terminating. There are only 4 values for the different values of B, I guess. B could be 0 through, wouldn't that be 5 values? Anyway, I have to go back and look at that. I thought there might be 5 values, but I guess there are only 4. Anyway, so that's symbolic execution, and we can do at least the slow version of symbolic execution. Actually, that ran fairly fast. I mean, this is a toy example, obviously, right? If you want to run this for a real application, that'd be different. And in practice, there are a variety of optimizations people use, and also people have figured out how to tie this to bytecode and stuff like that. So you don't have to encode an interpreter for the language or things like that. So still, what we can do is interesting because for an arbitrary language, you can write an interpreter for the language, implement the semantics, and get some symbolic execution. But in order to make this really efficient, we're going to have to use more tricks. And one thing that would be low-hanging fruit, and maybe Orchid could try, would be can we use finite domain constraints and make this more efficient, and make the code synthesis more efficient as well. And we can just get rid of that one obsceno by tagging the normal values coming back. So Orchid, you should be able to run all of this code in your version of miniKanren, I think. All right. So let me turn on screen sharing. All right, so that went longer than 15 minutes, right? But that's fine. I wanted to get into a little of the detail. Yeah, so have people seen symbolic execution before? It's something I've just been learning about recently, and that's pretty cool. And there's something called concolic execution, which is concrete symbolic execution, where you have so you're sort of mixing the concrete execution of the program with the symbolic execution of the program, and the first time I was seeing this stuff, I was like, well, miniKanren already does all this, right? So it's we just have to encode this, and I think having the while language makes it easier to see what's going on. But for whatever reason, you normally don't see symbolic execution for higher order languages. Maybe just because it's too computationally expensive or whatever. But now that we have a while interpreter, we can do a symbolic execution and start playing around with that. So that's kind of neat. And I think there are a bunch of other games we can play now that we have the symbolic execution stuff working. So Orchid, I'd be very happy to see what you come up with. Running this with finite domains. I think it should run better, is my prediction. Yeah. Any questions or comments about the while language, or implementing those semantics, or that interpreter, or the code synthesis, running backwards, symbolic execution? So it's this by example. I'm going to a MIT summer school on Monday, which is all about code synthesis, because area I'd like to start applying miniKanren to better. It's like, we can do it. It's not very efficient. People have figured out all sorts of tricks with the code synthesis stuff that seems to make it work much better. So one approach is to use type system to help direct things, and you might even tie in the type inferencer to the examples and things like that. There's been really cool work out of UPenn along those lines recently. I'll learn about that on Tuesday. I'll put a link to that paper in the chat also. But there's been a lot of really cool progress just in the last couple of years in code synthesis. I think a lot of that's been driven by better SAT and SMT solvers. So anyway, it's neat to see. It's a little humbling because there's been so much engineering in the SMT solvers that it's a little hard to compete with miniKanren, but I think in terms of generality, we do really well, and I think we probably can apply a bunch of the optimizations. So that'll be neat to explore with more and see what ideas we can apply to miniKanren and code synthesis. So, yeah. So that's while, and that's also symbolic execution, and if you're interested in that, there's also concollect execution, which you can also check out. All right. So let's see, it's 2:51. Do we want to try to tackle the macros, the first class macros, or getting a little too late? Orchid, is that oh, okay, that was a no from, have you seen a symbolic execution before? So if people want to play with macros, I'm down for that. It's up to me. Well, hey, I'll keep going. I mean, if I'm not working on this, I'm going to be working on miniKanren anyway, so it's all the same to me. Yeah, it's up to y'all. So what I said last time was, I thought the first class macro stuff had gone pretty well, and I suggested having someone else drive next time if we want to work on it. So I guess the question is there anyone who'd be interested and willing to drive to keep working on the first class macros? Or we could save the first class macros for another time. I know it's a lot to kind of bite off. Well, okay, so the other thing we could do is Orchid. Do you have your version of miniKanren online? Yeah. We could just try seeing if the finite domain constraints help with the while and the code synthesis and all that. Do you want to try that? All right. It's just a finite domain, though. Okay, so what does that mean? There's no arithmetic operations. Oh, okay. Oh, so this is for things like booleans and all that to make sure it composes. Is that correct? Ah, okay, okay. So, all right, I misunderstood. Okay, I thought this was going to give us the arithmetic stuff. Okay. Um, okay, Orchid did an experiment. Tried to rewrite the relational interpreter in Prolog. Okay, how did that go? In web CHR. So this is like a web-based version of the constraint handling rules, which implement disequality constraints. With the 2 to the inbound and the number of evaluation steps. Okay. I thought Prolog already has disequality constraints, isn't it? Did not produce any quines. Okay. Yeah, so that's an interesting topic to talk about. So my understanding is that the standard Prolog actually has disequality already as a built-in. I think the problem is that, oh, it has a bad disequality. Is it not relational? Ew. Oh, I didn't realize that. You can tell the var is fresh? Oh, that's not cool. That's not cool. Okay. Well, that's good to know. I didn't realize that. Okay, so you need to use something like constraint handling rules to add the relational negation, or the relational not equal. Oh, that's sad. That's sad. Okay. I had not realized that. Okay. Well, there are a couple other issues I think are tricky, right? So one is, okay, so first of all, NadaMN has come up with a fully tagged relational interpreter that doesn't use disequality constraints. So you don't need disequality constraints to do the relational interpreter if you use anything that's tagging. It's tagged, right? No coroutines. Okay, so yeah, so I was going to say the other thing is like you probably are going to run problems with the search, right? If you're going to use def for a search, it's probably not going to work well. So I think you're going to, well, there are two other things, at least. One is the search. And if you're not, okay, so you depth limited search, okay. So that should help as long as it's, yeah, so you should be able to see that. It might be really inefficient, I don't know. But you should be able to find it. The other thing that Michael Valentine was saying was that for quines, you actually need the occurs check. And I haven't tried this, but he was saying that if you remove the occurs check, if you try doing this in like miniKanren or something, you'll actually try to reify circular terms, and your program will diverge or whatever. So, and I haven't played around with that at all. But we could try it in miniKanren. We could easily like just remove the disequality constraint and see if our quines go in an infinite loop. Yeah, a lot of infinite programs might be quine. Yeah, so we could try that. Should we try that real quick? Let's give that a shot. That's something I wanted to play around with and just haven't tried. All right. Gene, put in a link. Prolog. Diff2, saying A and B are different terms. Yeah, diff2 looks like diff2 looks like the disequality constraint, right? Yeah. Yeah, so Orchid, did you see the diff2 constraint? That looks relational to me. I'll go ahead and bring that up. So, let's see. Yeah, so this is what showing. This is diff2 predicate Prolog. Let's see. The diff2 predicate provides a constraint saying that A and B are different terms. If A and B can never unify, diff2 succeeds deterministically. That's what it does in miniKanren. If A and B are identical, it fails immediately. That's what we do in miniKanren. And finally, if A and B can unify, goals are delayed that prevent A and B becoming equal. Yeah. Oh, I'm using attributed variables, which is what we're doing now, like a Valentine's new version of miniKanren. And also, David Nolan's version of miniKanren uses attributed variables for constraints also. Yeah, so that looks okay. I think the search and potentially the lack of curse check might be more of an issue. So let's try that. Let's find a version of scheme. Here we go. This looks like a good one. Yeah, it should be plenty, I think. All right, let's try loading this. Okay. So here we get a quine, that's sort of our canonical quine. All right. So let's go into miniKanren, and let's look for the occur check. Excess check. That's what we want. Let's come out that one. And let's just cons it up regardless. No occurs check anymore. Okay, let's make sure that the occurs check doesn't work anymore. Ah, so that succeeded. That should have failed because now X and list X are bound. And if I unify X and Y, or sorry, X and Q, yep, it diverges because the reifier is trying to print out an infinite term. Okay, so we've gotten rid of the occurs check. And let's try doing our, oh, wow, look at that. Is there any way to have it print infinite terms without dying? Well, you could certainly detect circularities, right? You could detect circularities, and there are versions of Prolog that do that, like Prolog 2 can handle circular terms. Yeah. Yeah, and in Scheme can handle circular terms as well and print those out. So you would have to have you'd have to be able to do that. So so like we can let's see. So define foo to be cons 3, 4, and let's set set car bang of foo to be foo, and yeah, so I just introduced the circularity there, and we can see the printer can handle it. And see, I should be able to set could or bang a foo to be foo. Yeah. Or I could set the could or bang a foo to be list containing foo. Yeah. Okay, so we could just handle circularities, and in fact, there is a version of miniKanren. If you go to miniKanren.org, there's a version of miniKanren that handles circularities. So let's see. Which one is it? Is it bKanren? Recursive miniKanren. There we go. Recursive miniKanren. Recursive miniKanren can handle circularities. And there's some interesting examples here of what happens when you can handle circularities. So I haven't really played around with this version of miniKanren, so if someone wants to check that out, or add circularity support, it totally makes sense to add circularity support. There's nothing wrong with it. This is perfectly fine to have answers like that, right? It just means that you've got a different sort of term language. So Prolog 2 is all about this. In Prolog 2, you can have these what are called rational terms, which are potentially infinite trees that you can represent finitely. So there's a long history in logic programming of being able to do that. So I find this really interesting with the evaluate, or sort of this, yeah. So it's a evaluate call because let's see if say I want to do hash t. So hash t is a quine, right? And hash f is a quine. Those are the first two quines we got back. Wow, that took a while. Okay. But we're apparently hitting something that's circular before we're hitting hash t or hash f, which is kind of astounding to me. And just to make sure that we actually are getting an answer, it's just we can't print it out. We can. Whoa, uh-oh. What is going on here? Now that's unexpected. That I had not anticipated. So, that is not a reifier problem because we're not reifying Q here. There's something deeper going on. I don't know. I guess there's something that's really interesting. I don't know why that's not working. There's something going on with our implementation of the interpreter that really is requiring deeply relying on the occurs check. It's not just at the reifier. Otherwise, this should have come back immediately with like hash t or hash f. There's something else going on. I don't know what it is. That's a mystery to me. Let's see. Orca says to evaluate an infinite term without quote in it, it has to evaluate the inside first. Oh, so it's actually getting into an infinite loop trying to evaluate one of the sub-expressions. An infinite term without quote. And to do that, it has to loop. Well, there's definitely looping behavior going on. Yeah, interesting. That is interesting. It'd be interesting to try to track that down a little more and try to figure out exactly what it's trying to, what term is it getting stuck on? Can we figure out what term it's running into? Should probably be able to print that out through recursive calls to evaluate. Try to see what's going on. Oh, I guess we can try that. Let's try printing out, see what's going on. I don't remember if I have any debugging aids here. Do I have like a... Nope. I don't have a print G. Okay, so we're going to write a little print macro here. Or a little print helper. And let's see. Let's grab that version. So we want to print value of S. And then we're going to apply a constraint store C to a dummy goal that just succeeds. And this should print out the substitution at this point when we're in eval expo. So let's see if that works. So let's try something simple. Let's just try valuing hash t. Okay. I guess we also want to see what the expression is, right? And, okay. We also want to project these things, I think. And we have to be a little careful. Ooh, the project as a walk star. This thing goes in an infinite loop. Wow, this is so tricky. So tricky. All right. No, well, looking at the constraint store should be fine. I guess we just can't look at X. Guess we really do have to just look at the substitution. Okay, that's fine. That's fine. We'll look at the substitution. All right. So let's see what happens when we try doing an infinite loop. Well, that didn't go very far, did it? That suggests to me that the problem isn't in eval expo. All right, so let's go ahead and make this a little nicer. Define print goal. Let's make it a macro. And syntax print G. So we're going to have like a little debugging macro here. And I guess we can give it a message. And then it's going to print out the substitution. Okay, so this will tell us when we're in eval expo, hopefully. Okay. So it looks to me like eval expo isn't where we're going in infinite loop. Could be in one of these other things. This is really somewhere where we could have much better debugging aids, right? I mean, our debugging technology is pretty weak right now in miniKanren. We can write these little goals at least, but it's for printing, but it's a little weak. All right, that might be enough to tell what's going on. I suppose these primitives might be causing problems also. Really? Am I missing something here? There's a recursion happening, we should get back in. Look up. Huh. Well, okay, this is also recursive. Am I doing anything wrong? What's going on? This is confusing me. I think I would see the... All right, let me try something else. It's a little simpler. Let's try evaluating cons of cons, quote A to quote B to quote C. That should make multiple calls. Yeah. Wow, we're getting stuck fast. This is bizarre. Maybe it's prim expo. I'm confused. So we're getting to this point. It's the only thing I know for sure. All right. So we'll do it the old-fashioned way. Quote. Quote. Is that what you were saying, Orchid? Something about quote? Oh, because the output value, because the output is in the input, right? So why is that a problem? Okay, so the substitution, let's look at the substitution. We have the variable q down to the list containing q. And now we're doing an absento. Oh, you know what? You know what? I think I know what the problem is. I think there are walk stars happening inside of this implementation. Just in reifier? Maybe? Huh. I don't understand. If they're only in the reifier, what if I remove the absento? Does it get any further? Does. Look at that. The absento is causing the infinite loop. Absento is doing this memcheck thing. All right. Look at this, recursive. That's it. This is like a walk star. This is equivalent to a walk star, so that circularity is making absento go into infinite loop. That's what it is. Wow. Okay. That's interesting. That's very interesting. So if we remove that absento call, then we actually get something back. We can't reify it because it's got an infinite loop in it still, but we do get something back. It's saying that Q is quote Q. And yeah, I guess that's a Quine. If you believe in infinite data structures. Okay. All right, so that's the problem. That's the problem. I wonder if that was what Michael was running into. So the problem was that absento. Very interesting. All right. Well, you can see the crude tools that I had to use to do this, right, with these print G things, print goals. That's pretty nasty. If anyone has better tooling or has ideas for better tooling to make it easier to work through these sorts of tracings, I for one would greatly appreciate it. This is, I guess I may as well keep the print G around. It's brushes there. Maybe a source interpreter could enable a nice debugger that lets you step. Yeah, an interpreter for miniKanren would be really nice. Definitely. All right, and then I'm going to change back the the excess check. All right, let's go back to the old one. Interesting. So that that explains why, at least in that version, we were running into infinite loops when we wrote the occurs check. I don't know if with the new version that Michael's been working on with the attributed variables, that might have a different sort of behavior. Okay, back to normal. All right. Well, I learned something there. Yeah. So that's one way to debug miniKanren when you're getting infinite loops, is to, or just in general when you're not sure what's going on in miniKanren, you can add these goals that are doing printing. But better tooling would be nice. All right. Unless we have anything else to talk about, I feel like this is probably a reasonable place to stop. Maybe next time or sometime soon we can finish up the first-class macros, or people will grow weary of that. Maybe I'll play with it on my own, or someone else can play with it. I feel like it should work. I don't see any reason it shouldn't work based on what we saw before. And they'd be fun to play around with and actually do macro synthesis, like macro synthesis by example. We kind of need. Okay, anything else? So I'll be in town next Sunday. I'll be between the Boston trip and a trip to Poland. I'll be talking about miniKanren at PolyConf. So I'm not going to have a whole lot of time, but I'll definitely plan on doing the hangout. I'll probably keep it pretty short on Sunday, just because I know I'm going to have prep for the trip. Yeah, thanks, Daniel, for joining us. Let's see, let me just check my calendar real quick. I've got a bunch of travel coming up, so yeah, so I can do next Sunday, and then no, I can't do the 5th, and then I can do the Sunday after that, and then I'm going to miss a Sunday, and then I'm going to miss a Sunday, and then I'm going to miss a Sunday, and then I'm going to miss a Sunday. I'm going to miss 4 Sundays in a row. And then I have a Sunday, and then I'm going to miss 3 more Sundays, and then it settles down a little bit. So, yeah. So we're going to get a little intermittent for a while, just due to traveling. All right. Well, thanks everyone for joining, and I think I'll stop the broadcast now, and if people want to talk about things or chat off air, then we can do that. Thanks everyone. And have a good weekend, and hope to see you next Sunday. Bye.